Anyway, now hopefully I have joined now. Okay, 48 students are there. Please send your WhatsApp message in the group, Kalyan.
Yes, sir.
Okay, are you able to see my screen?
Yes, sir.
Okay,
Yes,
guys.
sir.
Yeah, I mean, just recap first a couple of minutes because last week only we had the last Tuesday we come had a class. Okay, just recap, just a couple of minutes, then we go for the today topic. It will be very useful. Now, I mean, the soft now in the first chapter, now we are discussing the soft design keys and keys, and later we are going to discuss the couplings, different types of couplings. We already completed soft design, I mean, using solid shaft. But now we are going to discuss today the hollow shaft. And hollow shaft also the basic information we discussed in the last class. Now we are going to discuss the hollow shaft. Before entering into the hollow shaft discussion, just to recap the information what we discussed in the solid shaft. Now, solid shaft, the design is based on that strength basis, I mean, torsional rigidity or lateral rigidity basis, and ASME code approach. This is the three ways we have been discussed the solid soft design and the corresponding problem we discussed. Now, the soft is subjected to tensile load, static load. This is sigma t is equal to 4p by 5d squared. From this, we able to find the diameter of the shaft, and this is the when the shaft only subjected to pure bending. Then we are going to use this formula for finding the, I mean, diameter of the shaft. When the shaft is subjected to pure torsion, we are going to use this formula to find the diameter of the shaft. Right? But when the shaft is subjected to combined both effect, I mean, normal stress sigma b, I mean, bending stress also under normal stress, and the shaft is subject to twisting moment, then torsion shear, then the Mohr circle is important role for our shaft design. hence we are using Hence we are using this Mohr circle concept. Mohr circle, I mean, concept here. Mohr circle concept, based on that we already studied sigma is equal to sigma x by 2 plus sigma whole square root of sigma x by 2 whole square plus tau square. This is nothing but maximum principal stress. This is nothing but maximum shear stress. Right now, I mean, as we discussed, right here we are now we combined bending and torsion, then substitute this sigma b and sigma t, sigma b and tau, sorry, sigma b and tau in these two equation. These two equations, then we are going to get this one. Sigma 1 is equal to 16 by pi d cube into mb plus square root of mb square plus mt square. Now similarly, now sigma 1 is equal to this. What is sigma 1? Sigma 1 is equal to nothing but SYT, yield strength divided by factor of safety, that is defining the permissible value of sigma 1. I mean, instead of sigma 1 we are considering SYT divided by Fs in this place. Similarly, maximum shear stress theory, right? Maximum shear stress theory, I mean, use this formula and substitute these values. We are going to get finally this 16 divided by pi d cube in square root of mb squared mt square. Now, this is the term is nothing but equivalent bending moment. This is the term is nothing but equivalent torsion moment. In the right and left hand side, tau max is nothing but shear yield divided by factor of safety. This shear yield, we came to know that in the design of mesh elements, 0.5 times of SUIT divided by Fs. Okay. Now this is a permissible value. From these relations, we are able to find out the diameter of the shaft, especially this formula suitable for brittle material. I mean, maximum principal stress theory, MPST, suitable for brittle material, maximum stress theory suitable for ductile material. Now, I mean, later, I mean, torsional rigidity. I mean, this is a torsion rigidity coming from that governing equation T by J is equal to G theta by L. The T by J is nothing but the T instead of T I am considering MT. From these relations, now theta is equal to, we converted in terms of radians from radians to degree, then 180 divided by pi into MT divided by L by GJ. From the J is nothing but polar moment of inertia, then pi d power 4 divided by 32. From this relation, we are able to find out this, I mean, torsion rigidity of this shaft based on the shaft dimension design based on the torsion rigidity. Now, ASME code approach, ASME code approach also nothing but is this, the design data book. Here we used tau max is equal to 0.3 times of SYT. They've gone to some practical studies and experimental studies from the laboratory. Then finally came to know that tau max is equal to 0.3 times SYT and tau max is equal to 0.18 times of SUT. I mean, from these two relations, which one is the lowest value that will be considered for the permissible stress value. Now here, I mean, suppose this is equation for when the key is not presented. Key is not present in the shaft. Suppose key is presented, which value is the minimum value from these two relations? That value again multiplied with 0.75. Again multiplied with 0.75. Then that can be a permissible stress value. Okay. Now in the ASME code approach, now we are introducing the factors KB and KT. I mean, combined shock and fatigue factors, KB and KT. I mean, the same formula, whatever we discussed, equivalent torsional moment, equivalent bending moment, but we are introducing KB and KT in this equation. That's all. Okay. Now this is, we discussed, I mean, load is gradually applied. KB is equal to 1.5, KT is equal to 1. I mean, similarly, load is suddenly applied. KB is equal to 1.5 to 2. KT is equal to 1 to 1.5. Load is suddenly applied, heavy shock 2 to 3 and 1.53. Because this is, whatever we discussed, this is a gradually applied load. But here, now, I mean, whatever this is, we are introducing the KB factor. When suddenly applied load and heavily shock load, during that time, I mean, during that time, we are considering that KB and KT value 1.2 to 1.5 3 in KB value, 1 to 2, 3 in KT value. Okay, this is the problems we discussed in the last class. Now, just whatever we discussed, this derivation, I mean, equivalent torsion moment, equivalent bending moment, okay, and ASME code approach, and torsion rigidity based, I mean, soft dimension, soft design. Those things, please keep in mind. That will be very useful when now we are going to discuss that. I mean, our hollow shaft now. Right now, I come to this hollow shaft. I think some of the basics we discussed in the last class. Okay, in the last class we discussed some of the basics. Now we start from this hollow shaft design. Then we discuss the problem corresponding hollow shaft design. We discuss the problems. Okay. Now this is the page number. Okay. Now this is the see here. I mean, this is the same equation. This is the same governing equation of torsion. I mean, derived from the same governing equation of bending. Right. Now, here we discussed, these are the informations. R equal to 0, sigma B is equal to 0, tau is equal to 0. I hope that we will discuss in this basic concept, and applications also will discuss. Now we directly enter into the, I mean, derivation. Now, I mean, this is a shaft subjected to bending. Then you just imagine it. The shaft you take, and the front view, this is like that. In the side view, in the cross section view, this is like that. Now this is the, in the cross section view, in the, I have shown you some, I mean, some test specimen I shown you in the last. I have shown you in the last class. Okay, this is a torsion moment. This is a bending moment. The upper layer, when the bending moment is acting here like this, then upper layer is the compressive. I mean, bottom layer is a tensile. Similarly, in the cross section, the mean shaft is subjected to torsion. I mean, top layer is tau is here, and bottom layer is tau is here. It looks like, I mean, is similar to our Mohr circle, right? Yeah, similar to our Morse circle. All right. Now I come to this derivation. We considered, because we are using considering the solid hollow shaft, sorry, hollow shaft, the ratio di inner diameter, inner diameter di and outer diameter d naught. Now di by d naught is equal to c. The c value is less than 1. Now come to this. This is direct tensile force. I mean sigma d tensile stress is equal to p by pi by 4 d squared for force by area. Then substitute here. Now di squared. In this place, I am introducing my c value. C is nothing but c di by d naught. Then c squared into d naught squared. Okay, d squared into d naught squared. Finally, I have taken out 4p divided by pi d naught squared into 1 minus c squared. This is for when the shaft subject to static load in tensile behavior. Okay, then this formula can be used to design or define our diameter of the shaft d naught. Okay, now I come to this. Shaft is subjected to bending moment. Shaft is subjected to bending moment, and bending says now sigma b is equal to mb into I divided by I. Now again use this I is equal to, we are very well known, pi d naught power 4 minus di power 4 divided by 64. Here again use this c ratio. Again use this c ratio. Then I is equal to pi d naught power 4 into 1 minus c power 4 divided by 64. This is I. Now what is y here? This is y is nothing but m by I is equal to sigma b by y. This is the governing equation of bending, right? Down that y is nothing but d naught by 2. Now this is a relation. Now we know the b relation. Moment of inertia I. This is now y value. Then substitute in this equation, in this our governing equation, find governing equation, sigma b is equal to, we are going to get this. Substitute here this equation, mb into y divided by I. Y we know d naught by 2, I we know here in terms of c. Then substitute here, we are going to get this equation, sigma b is equal to 32 mp divided by pi into d naught cube minus 1 minus c power 4. Suppose c is equal to 0, c is equal to 0, then this is going to be solid shaft. When c is going to 0, it is the satisfying with the solid shaft. Now I come to this similar manner. This is a torsion equation. What is this? R is equal to nothing but d naught by 2. Okay, 1 minute. R is equal to nothing but d naught by 2. And now polar moment of inertia is equal to, you are very well known about this formula, pi d naught power 4 into 1 minus c power 4 divided by 32. From this is one relation, so r is equal to d naught by 2. From these two relation, substitute this e and f into this our governing equation, where we obtained this tau is equal to mtr divided by j. Find, we are going to get this tau in terms of c. Okay, now we know the sigma b normal stress, we know the tau in shear stress. Now again we are going to apply our Mohr-Seifel concept here, maximum principal stress theory and maximum shear stress theory concept here, finding the appropriate equation for designing the shaft, or for defining the diameter of the shaft. Now see here, very important relations, very important statement here they are given. The construction of the Mohr circle diagram for the hollow shaft is similar to the Mohr circle for the solid shaft. Okay. Now sigma x is normal stress, right? Sigma x is normal stress. Sigma b also under normal stress. Suppose the shaft is subjected to tensile load. Suppose the shaft is subjected to simultaneously bending. Then we are considering the total normal stress is equal to sigma t plus sigma b. Total normal stress. Suppose in the case of shaft subjected to combination of bending and torsion moment, it's no direct tensile. Hence sigma x is equal to, we are considering sigma b only. Sigma b only. Okay. Now see, based on the maximum principal stress, substitute this value sigma x. Now sigma x is equal to nothing but sigma x is equal to sigma b. So whatever we derived here, substitute this 9.8, 9.18 and 9.19 in this equation, 9.20. Finally, we are going to find the relations. That relation can be used to define the diameter of the shaft. Similarly, the equation 9.18 and 9.19 again substitute our maximum shear stress theory equations. So tau max is equal to square root of sigma max by 2 plus tau square. Then we are going to obtain the equation. That equation can be used for defining the diameter of the shaft when the shaft is assumed to be shaft design is based on that tau max. Okay. Now see here, I mean, whatever we discussed earlier slide, I told you the 9.18 and 9.19 substitute this equation. Then with sigma 1, we are getting this. We are getting this equation finally. Sigma 1 is equal to 16 divided by pi d, 16 divided by pi d naught cube into 1 minus c power 4. This sigma 1. Now, suppose again you see this the same equation, which will satisfy with the solid shaft when c is equal to 0. Substitute c is equal to 0. This is satisfying with the solid shaft. Similarly, I mean, here sigma 1 is nothing but our earlier whatever we discussed, SYT divided by FOS, factor of safety. Now this is the left hand side of this equation. This is a permissible sigma 1, SYT divided by FS. Now come to this torsional. Finally, we are going to get this. Now come to the maximum stress theory. Now see here also we are getting 16 divided by pi d naught cube into 1 minus c power 4 into whole square root of mb squared plus mt squared. Now when you put c is equal to 0, this is a satisfying the solid shaft, I mean based on the tau max. Okay, now here also the left hand side, tau max is nothing but the permissible stress value 0.5 times of SYT divided by FOS. Okay, this is the two equations very important while designing the shaft, I mean while defining the diameter of the hollow shaft. Okay, now torsional rigidity. Earlier case we considered the based on the strength. In the strength, based on the strength, based on the strength, we are assumed that, I mean, the shaft subjected into bending and the shaft subjected into torsion. Now we are considering the based on the torsional rigidity. The torsional rigidity. So in this case here, the shaft is the design of the hollow shaft is on the basis of the torsional rigidity is governed. I mean, here the angle of twist per meter length. When we are designing the shaft, we came to know when we are designing the shaft. Suppose I am defining. Suppose I have the shaft. Just I draw it. Suppose I have the shaft, 1 meter shaft. I mean, I'm going to use this shaft for some application for transmission. During that time, the shaft angle of twist, I know that. I mean, the shaft is going to happen this much angle of twist per meter length. I know that. Then once I know that angle of twist, then whatever we discuss in the solid shaft, similar manner, we are going to introduce here. Everything same. I mean, this J value, sorry, the J value only different. I mean, J is equal to pi d naught per 4 minus di per 4 divided by 32. Substitute here. I mean, we can write in terms of C here. Finally, we are getting, I mean, the polar moment of inertia, J, substitute this main equation. Finally, we are getting theta is equal to 584 mt L divided by GD naught per 4 into 1 minus C per 4. Suppose again you put here C is equal to 0. This is satisfying the solid shaft. Okay. Now we come to the problem. A hollow shaft, a transmission shaft having inside diameter 0.6 times. I mean 0.6 times. 0.6 times means nothing but a C value. Di by d naught is equal to 0.6 and is made of a plain carbon steel 40C8, what we discussed in the, I mean, earlier semester in DME. 40C8, I mean, it's a material notation. Okay, 40C8. I mean, SYT is equal to 380 Newton per mm squared yield strength. Okay, and factor of safety FS is 3. The belt pulley is, I mean, the pulley dimension is given 1 meter. Okay, I mean, mounted on the shaft, which is war hanging in the left hand side of the bearing. Okay, Now this is the left hand side bearing. Okay, I'll say you. I will come to you later. Left hand side, they mean overhanging left hand side of the bearing from the distance of 250 mm. This is the left hand side fixed bearing. Okay, bearing. Okay, now 250 mm. Now the belt is vertical. Now here they clearly told, I mean, only in the problem, only in the design problem, you are going to get this problem only, this diagram only. You may not get this one. Okay, now and the pulley is, I mean, that the belt pulley is vertical and transmit the power to the machine shaft below the pulley. The tension on the tight side and slack sides are given. This is a P1 is 3 Newton, 3 kilonewton, and P2 is the 1 kilonewton. While the weight of the pulley is, now we are considering this is the pulley weight, now 500 Newton. The angle of warp, angle of the warp of the belt on the pulley is 180 degree. 180 degree. Because now, as I told you that only this problem, this figure only given to you, then during that time, now based on this angle also we came to know that, I mean, only vertical load is acting. Suppose 180 degree, maybe 7, I mean, suppose 130 degree, then it will be a combination of horizontal load and vertical load is playing role. But 180 degree means that vertical load is playing in the pulley. That's what indirectly they have given data like that. Now I come to the problem. Now, I mean, SIT is given 380 Newton per mm squared, and Fs given, and C is given. C is equal to di by d naught is equal to 0.6, and P1 and P2 given. Then pulley diameter, pulley one weight of the pulley is given. Now this is the diameter of the pulley is given. Finally, this is our 63.33 is Newton per mm permissible stress value. Right now, see here, this is a very simple problem. This is the cantilever. It looks like cantilever beam approach now, right? Cantilever beam approach. This is the length is given 250 mm, right? Now the, I mean, load is acting downward. Then you already well studied about this. I mean, bending moment shear force diagram of the simply cantilever beam. Okay, now this is the bending moment. The free end is 0, the fixed end is by maximum bending moment here. Okay, now what is the bending moment? Yes, yes, someone is calling. Hello, Kalyan.
No one, sir.
Okay, now first we have to find out the torsional moment. I mean, here the belt, I mean, the belt and pulley we already discussed in the earlier solid soft problem. P1 minus P2 into diameter of the shaft, I mean, radius of the shaft, not diameter of the shaft. From these relations, we know MT. What is the torsion moment? Then, I mean, we know P1, P2, and or also we know the problem is given 1000 mm. Then we able to find out MT. Now, MT is constant at the bearing as well as the where the pulley is located. Now these two informations we able to use to define our diameter of the shaft. Now see here, I mean, see here tau max, here permissible maximum shear stress value is given. I mean, tau max 16 divided by pi d naught cube into 1 minus c power 4. Substitute here mb value, bending moment value and torsion moment value. Finally we are going to get d naught, shaft outer diameter of the shaft is nearly 52 mm, and the inner diameter of the shaft is already they have given in the problem. I mean, C is nothing but 0.6. Then we are able to find out this diameter, inner diameter is nothing but, I mean, nearly 31 mm. Okay, now we move to the keys. Yeah, please go ahead. If you have any doubt, please go ahead. Because, I mean, whatever we discussed the problem in the early, the same problem it can be considered in the hollow shaft. Hollow shaft. Please be careful. But that's what I'm not going more problem in that. Whatever we discussed the problems here. Okay. The same problem I can ask as a hollow shaft. The formula is same. Only the important things here. Then I mean that is C value is important role. C value, whatever here, the C value is important role. The same problem we can ask in the form of hollow shaft. This problem also we can ask in the form of hollow shaft. I mean, same approach. Only you have to concentrate the C value, how to where and how to, I mean, substitute the C values. You should practice. Okay, then remaining things are same. Now, I come to this next keys. I mean, before entering into the keys, I'm asking you that keys. Can you give me the example and where we are using keys? Yeah, please. Keys.
In gearbox, sir.
Yeah, gearbox. Okay, gearbox. Gearbox. Okay. Yeah, gearbox also using key. Okay. Yeah, simple example. Any other simple example, please? Have you seen your cycles also? Bicycle.
Yes, sir.
Hmm.
Pedals.
And yeah, tell me, Pa.
Sir, where the pedals were connected to the shaft.
Yes, 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 yes. Okay. So keys is very important role. I mean, only defining the as in the, I mean, very first class or second class, I clearly told that with the shaft, with the pulleys, we can't do power transmission. When we want to transmit the power from shaft to one place to another place, the the pulley or gear drive, right? Pulleys or gear drive mechanism, the gear should be connected properly on the shaft. Otherwise, with then only we can do proper power transmission. Suppose the gear is connected on the shaft without without using key, without welding, without screwing, then what will happen? The, I mean, the shaft will rotate alone. Then the shaft rotate alone, which will not transmit the power. Hence, we are using the key. Now, come to the keys here. So, we need keys for power transmission. We need a key component. We need a pulley. We need a shaft. We need a bearing. We need a belt. When we are using pulley, we need a belt. When we are using, I mean, gear, we need a pinion and gear, right? These are the components. Without this component, we cannot do power transmission. In this chapter, we are going to discuss the keys, we are going to discuss shaft, and we are going to discuss what are the component, coupling components. I mean, keys. Later, we are going to discuss the couplings, different types of couplings. That's what in the first chapter we are discussing shaft and the keys and couplings. We are giving more importance. Later chapters we are going to discuss the bearings. We are going to discuss the gears in the later subject, later chapter. Okay. Now see here, keys. I have given this some, I mean, basic explanation. Keys can be used as a machine element, which can be used to connect the transmission of the shaft to the rotating machine element. I mean, the keys can be used to connect the pulleys, gears, and sprockets or flywheels with the shaft. Without the keys, these things cannot be, I mean, these things, I mean, the power transmission cannot be done properly. Okay, the keys consisting of shaft, hub. I mean, see here, see, this is our hub. I mean, we are going to discuss later. The hub also is one, I mean, under one type of coupling. Now the hub is here, the shaft is here, this is shaft, this is hub, right? This is a key. Now, suppose without a key, I inserted the shaft inside the hub. When the shaft is connected to the motor one end, right, one end, then what will happen? The power transmission cannot be done without the keyways, because this hub will be connected through the keys. Then only the power transmission can be done. So this is 1, 2, 3. Now the keyways. I mean, the part of the key is going to sit on the hub, and part of the key is going to sit on the part of the key. I mean, this part of the keys are going to be sitting on the hub. This portion going to be sitting on the shaft. Okay, the top portion is going to sitting on the hub. So the power transmission can be easily now done, can be easily transmitted. Now we will see the brief explanation of the keys. The primary function of the key is to transmit the torque from the shaft to hub matting element and vice versa. It may be I may apply the force in the, I may apply the rotary motion in the hub also. That's what. The second function of the key is to prevent the relative rotary motion, prevent the relative rotational motion between the shaft and hub. I mean, now without the keys, I told you that. I mean, it may be a self rotation. Without the keys, only the shaft will be a self rotation. Then it won't be a transmit the power. Hence, that's what prevent the relative rotary motion, rotational motion between the shaft and hub. Okay. I mean, the keys are used to connect the machine element like gear or pulley or flywheels, whatever. Okay. Now we are going to discuss in different types of keys here and here. I mean, some of the keys, I mean, the keys prevent the axial motion also. The keys are prevent the axial motion between the two elements, except in case of feather and splined connection. I mean, the splined connections we are using inside the gearbox. I mean, very useful for this mechanism for changing or accessing the gears from gear 1 to gear 5, or gear from low speed gear to top gear, or back gear. Okay, this is the splints mostly we are using in the gearbox. Now we see one by one. Now that's what I told you. I mean, now, I mean, few more points I would like to convey here. The key is inserted between the shaft and hub. In the simple manner, I am telling that the keys is inserted between the shaft and hub, so hub of the pulley, in order to prevent the relative motion. Okay. The second point, mostly inserted parallel to the axis of the shaft. I mean, the key is always mostly inserted parallel to the axis of the shaft. I mean, this is considered as a temporary fastenings or temporary joining. Okay, this is not a permanent joining. And the key is, you may expect this kind of questions in the objective. Okay, the key is subjected to crushing and steering stress. How the key is subjected to crushing and steering stress? This portion of the key, now, I mean, this portion is going to be subjected into shear or crushing. Whatever I have done in I mean, cross line, this portion is subjected to crushing or shear. I'm asking you that. Please, guys, reflect. See, this portion, the top portion, going to be subjected to shear or crushing.
Shear, sir.
Yeah, exactly. The side portion,
Crushing, sir.
crushing. Yeah, thank you. Just to keep in mind, when we are going to discuss this in derivations, it will be very useful. You can easily understand. That's what I'm feeding this information here itself. Okay, this portion is going to be subjected to shear. This portion, part of the portion, subjected to crushing, because the top portion, bottom portion is sitting on the shaft, hence crushing. The top portion sitting on the hub also comes subjected into crushing. Okay. These are the information, just keep in mind. Now, the keys are subjected to crushing and steering force. Then how the power transmission is happening here? The power transmission happening from shaft to pulley, shaft to keys, then it will be hub or pulley with help of steering force and crushing force. The power is transmitted from shaft to hub with the help of the crushing and steering force. Crushing and steering effect. Due to crushing and steering effect, the power is transmitted from shaft to hub or shaft to pulley through keys. Now I come to these different types of keys. Now, and I mean, one more thing, the keyways. Actually, keys, we are providing the slot. That is called a keyway. This is the keyway. The keyways are manufactured. I mean, made with help of the. I mean, made with help of which way? Which type of mechanism? The keyways are cut by the vertical or horizontal. Which mechanism? Which machine? Lathe machine, drilling machine, which machine? I mean, milling cutter. Which one we are using for slotting machine? Which one we are using for making keyways?
Milling, sir.
Yes, exactly. Yeah. Now we come to this different types of gears. Now uh, there are, first we see this. I tell you the different types of gears. Then we discuss one by one. There are 7 keys are available. One is sunk keys. Second one is saddle key. I mean, third one is tangent keys. Fourth one is round keys. Fifth one is square and flat keys. Now, sixth one is Kennedy keys. And seventh one is splints. Okay. Now, one by one, we will see that. Now, I mean, in keys are made of plain carbon steel. Keep in mind. And in order to withstanding the shear and compressive stress, I mean, as per the Indian standards, the tensile stress for the keys we are considering up to, I mean, 600 Newton per mm square. 600 Newton per mm square. I mean, should not be less than that. Okay, 600 Newton per mm square. Plain carbon steel. Most of the keys we are preparing with the plain carbon steel. And now I'm asking that very good question. Now, suppose now which material I mean, suppose soft is there, hub is there, key is there. I mean, which material should be better than, which material should be more harder and it will be more withstanding more stress value, withstanding more power transmission? Either key or shaft or hub. Which one is withstanding more power and more strength? Or either key or shaft, or which material we should concentrate more? Either key material or shaft material or hub. You tell me.
Shaft.
No, pa.
Key.
Key,
Key
sir.
only. For example, now my key, once a failure, then we can easily replace it. And the cost of the components also very less. Right? Key, once the key is getting failure. Suppose now shaft is failure, then the shaft will be connected maybe the engine or maybe the I mean from the motor, then it will be a more problem. I mean, replacing the shaft and the cost of the shaft will be more. Hence, I mean, the key design is very important. Based on the crushing, based on the steering stress of the key, we are going to define the power transmission. Suppose any failure happened from the, I mean, once the key is, for example, the key is broken during power transmission, we can stop the mechanism easily. It can be dismantled and again it can be engaged new keys. Then cost of the components less price and easily it can be replaced. Hence, that's what we are going to concentrate. Keys is one of the important role in our design. Okay. Now come to the different types of keys. See here. I mean, the selection of the keys based on the power to be transmitted, also thickness of the fit and stability connection. Stability connection. First, we discuss these types of key first. Now, this is the now. I mean, see here. This is the hollow shuttle key and flat shuttle key. This is hollow shuttle key. This is a flat shuttle key. Now, now shuttle key, only the keyways are provided on the hub only. Please, very important. You may expect this type of question in the objective. Shuttle key, I mean, only the keyways presented on the hub only. Hub only. Now see here, this in the shuttle key, two types: hollow shuttle key and a flat shuttle key. I mean, this hollow shuttle key is nothing but this is a small arc in design along the width of the key. Now the arc is equivalent to diameter is arc diameter is equivalent to our shaft diameter. Okay, this is the hollow shuttle key. This is a flat shuttle key. Now, based on the geometry, based on this key design geometry, we are saying that hollow shuttle key and flat shuttle key, which fits on the key of the hub only. And the light, I mean, where we are using, I mean, hollow shuttle key and flat shuttle key we can use in light duty and low power transmission. Here through the frictional resistance. Frictional resistance. Now I come to the sunk key. In the sunk key, now one by one I will discuss what are the sunk keys. Okay, now sunk keys. Now sunk keys. I mean, this is the sunk. I mean, sunk key, square key and flat key under the sunk key. Now this is the square key and flat key. Most of the industries we are using square key and square key, or I mean flat key. This is a rectangle key. This is square key for heavy duty applications, and in generally in industrial machinery we are using this type of key. Here no slip occur. Here no slip occur. But in shuttle key, is it slip is possible or not? In shuttle key, yeah, please someone reflect. In this key, no slip. But what about this key? Slip is possible or not? Please reflect.
Yes, sir, possible.
What?
Possible, sir.
Yeah. I mean, you may expect this type of questions in the objective. Okay, here slip is possible. Here, no slip. Now I come to the hip gutted key. Now, before going to the hip gutted key, I would like to give some more explanations about these keys. 1 minute. I note down some of the points. Yeah, now see here. Yeah. Sunk key. Sunk key, I mean the square key and rectangular key are under sunk key. Now hip gutted key also under sunk key. I mean, only the design is like that. I mean, when we are using such a kind of design, this is called hip gutted key. This key can be easily engaged and can be easily disengaged from the shaft and pulley. This type of key. I mean, this is the form of sunk key. It's a removable, easily engaged. And this is a light duty, and I mean slides and gear shifting. We are using this type of key. Now I come to the feather key. I mean, this is also flat key, square key, rectangular key, and hip gutted key are under sunk key categories. Now I come to this. Parallel. Okay, first we discuss the feather key. Now feather key is the form of sunk. This is also under the category of sunk key. This is a parallel key. I mean, where we are using loose fitting and light duty, we are using this key. But here you see here they provided some arrangement. We are using screw. But I mean, once we are inserting the keys here, we are using the screws to tightening the keys to avoid the, I mean, any direction, to avoid the lateral or axial movement of the key. Okay, this is a feather key. Now Woodruff key also under the sunk key category. This is semicircular key like this. Now I mean, this is wherever self alignment is going to happen, that place we are using this type of key, especially machine tools and automobiles. We are using this type of key. Now I come to this feather key. Feather key, some more points I tell you that. Now, I mean, this feather key is attached on the machine pair, member of the pair. It's a permit the relative. So I would like to say some more points. I mean, permits a relative axial movement, also known as the feather key. It is also this splined type parallel key, which I mean turning movement and axial movement. Okay, it is a fastened the shaft with the help of these screws. It is a fastened with the shaft with the help of these screws. Okay, this is a Woodruff key. We are using light power transmission Woodruff key. This is also under sunk key. But especially wherever self alignment is there, we are using this type of keys. And come to this is Kennedy key. I mean, Kennedy key also similar to square key, but the guy who found this concept to better power transmission, that is called kinetic key. Here the two keys are oriented 90 degree between them. See here, with respect to a vertical axis 45 degree oriented. With respect to two keys, the angle is 90 degree. Now later we are going to discuss this, how this arrangement, how this type of design is better as compared to our square key. We will discuss later in the derivation. So but I mean the standard concept is kinetic keys, the two square keys must be connected in, I mean, 40 degree orientation with respect to vertical axis of the shaft. Vertical axis of the shaft. Okay. Now you may expect this type of question in the objective. No splints. It is invalid internal part of the shaft. Axial movement is possible. Now, I mean, this is especially we are using the gearbox for shifting the gears. Okay. Now, I mean, this is the berth key. Berth is the keys bottom two corner. I mean, the corners of the any two corners of the keys is beveled and beveled. This type of key is the berth key. Okay, berth key. This is a double beveling. Ensure that the key will be fitted tightly. This is a tight fit. For we want to tight fit this type of key we are using for the power transmission. Now Levis key. Now Levis key also. I mean, this is anyway, this type of key we are not going to discuss more. Only we are going to concentrate on flat key and Kennedy's keys. Okay, mostly we are going to concentrate flat keys only. Remaining things are same only. I mean, these are the more expensive but offer excellent service. They may be used for the single or double key. You see here, based on the rotation, we have to define the position of the key. Okay. Now I come to this some derivation sunk keys. What is sunk keys? I mean, what are the keys under sunk keys? Square key, rectangular key, hip guarded key, and feather key. Okay, and woodruff key. These are under sunk keys. 1, 2, 3, 4, 5. These are under sunk keys. Okay, this is shuttle key. Now here this key only is subjected to, I mean, subjected to frictional resistance, this shuttle key. But a square key, I mean, especially sunk key. So under sunk key, there are different types of keys: square key, rectangle key, hip guarded key, and feather key and woodruff key. But this square under sunk key, most of sunk key is mostly, I mean, shearing force and crushing force are acting for the power transmission. Very important. Okay. Now I come to this some of the basic design of the keys. Now this is now, I mean, in the square key, B is equal to H is equal to D by 4. The D is nothing but now diameter of the shaft, D by 4. I mean, this is 1.5 times. I mean, the length of the key is 1.5 times of the diameter. Okay, this is the diameter of the key. I mean, width of the key or breadth of the key. This is height of the key. Both are same in square key. And length of the key is 1.5 times diameter of the key. Now rectangular key B is equal to D by 4. Here only this is a different. Width of the key is D by 4. Here also same. But the length of the key is the same. Only height of the key is D by 6. D by 6. This is the rectangular key. Now we come to the design of the square and flat keys. Design of the square and flat key. Now we are going to discuss. Sorry. Now see here. Now the shaft is here. This is shaft. 1 minute. Just a minute. Yeah.
Sir,
Yeah. Tell me, Ban.
time up, sir. We have another class by lunch.
How many students are there?
69.
69. Only okay. Yeah. Can you share me the attendance?
Yes, sir. I will share.
Okay. Stop here. Tomorrow we are going to finish this keys and couplings. I mean, only these two slides. Okay. Then keys problem we are going to discuss. There are a couple of problems only we are going to discuss in the keys. Then we are going to move to couplings. So in this week, we have to complete the first chapter. We have to start the second chapter. Okay?
Yes, sir.
Yeah, please go ahead. If you have any doubt, please go ahead.
No doubt, sir.
Okay, ba. Thank you.
Thank you, sir.
Thank you, guys. Kalyan, send the WhatsApp message. The attendance also to 67 or 68 people.
Yes, sir.
So still 20 people are not attending the class.
Uh, yes, sir. I will mail it.
Okay. Anyone received all 6 videos? Earlier 5 videos? Any issues? No one
Yes,
has
sir.
any issue, no? Already I gave access.
Yes, sir.
Last
I
week
received.
itself. Okay, guys. Thank you.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, everyone.